So students, today I will take this case of motional EMF, meaning that even when there is no flux change in a closed loop, there is a conducting rod. If any conducting rod is made to move perpendicular to the field lines, if it is moving perpendicular to the field lines, then for any conducting rod, मान लो ये हमने conducting rod ले लिया और इसको perpendicular to field lines move करा दिया. If this rod is moving and field lines are up, तो ये field lines को क्या करेगा? Cut करेगा. तो once it is cutting the field lines like this, जैसे grass cutter होता, so once it is cutting the field lines, means field lines and length of the rod both are perpendicular. तो आप देखिए velocity of the rod आपकी तरफ ऐसे जा रही है. Velocity of the rod, length of the rod and field lines, तीनों वेक्टर आपस में क्या हो गए? Perpendicular. If it happens, then what will happen? There will be some induced EMF developed along the length of the rod, meaning that there is no flux change, meaning that there is no bound area, area bound नहीं है. फिर भी अगर ये फील्ड लाइंस को कट कर रहा है तो देयर इज अ प्रॉपर्टी ऑफ induced EMF developed in the length of rod. Why that happens? Because of the moving electrons. The electrons are there in the material, and if I am moving it like this, so due to motion of rod, V is along this direction, V cross B, field is say up, so V cross B, positive charge पे force, it will be towards right. So this end will be positively charged and this end will be negatively charged. V cross B, आप देखिए velocity is in this direction along you, field lines are up, so V cross B will create a positive charge force here. So this end will become positive and other end will become negative. The charges, once they are accumulated at the two ends of rod, that will create a potential difference, and that potential difference and field created will get the polarity across the two ends. That thing we'll see in the detail. So this factor I am going to find is motional EMF. What I will do? Motional EMF in conducting rod. EMF in conducting rod. Even when there is no flux change, means there is no closed loop arrangement. Basic cause is the field lines are being cut. Say this is the conducting rod, this is the end P, this is Q. Conducting rod is having the length L and is moving with velocity V. And say the magnetic field lines here, they are perpendicular to the length. No? Say magnetic field lines are perpendicular to the length. Say downward direction, these are the field lines. Once this conducting rod is moving, so they have the free electrons. This conducting rod will have the free electrons and charges. So what will happen? Field lines are downward, you apply the magnetic force. I know this magnetic force is what? This magnetic force is Q times V cross B. This will happen, Q times V cross B. Charges can be of two types, either for the positive or for negative. For both the charges, direction of force will also be opposite, meaning that for positive charge, V cross B, force is up, means all the positive charge particles, they will be deposited here, and negative charges, they will move like this. So there is a polarization developed in the length of rod. Now the moving forces, if it happens, what I say, F magnetic, and this magnetic force, if you see, this magnetic force will be E, the charge of the proton, into V into B into sine 90 degree. So this is the magnetic force developed on the charges, and they will move. Positive charges will move in this direction. Magnetic force will be in this direction for positive charge, negative charge downward. Subsequently, what will happen? There will be an electric field developed. An electric field will be developed in the downward direction due to separation of charges. Initially, these charges, they will get separated, and a stage will happen once this E V cross B, which is acting upward on the rod, it will be balanced by electric force Q into E downward. Means once the charges are getting separated, some field will be developed. So this electric field, if I say the electric field is in the downward direction, so QE, force on the positive charge, if I say QE, force on the positive charge will be downward. The stage will happen when these two forces can balance. So I will say what it is, E into V into B, and that is equal to, this is also E into capital E. Capital E is for the field and small is for the charge, either for positive or negative charges. What I will say, this maximum value of electric field will be V into B, correct? And electric field is a vector quantity. If I go like that, simultaneously two forces are acting, that is called Lorentz force, and they can balance each other, the Lorentz force value. E is equal to V cross B. So net potential difference developed across the length of rod, that will be E dot L, and that will be your, here if I say it is B V into L. So potential difference developed along the length of rod is this value I can apply, correct? Initially magnetic force will be dominating. In the first case I can say initially you can take that F magnetic, the magnetic force F magnetic will be greater than F electric, but charges start accumulating, more and more charges are accumulating. After a certain moment, maximum charge will be developed across the two ends, and the field developed will be also maximum. When the maximum field is there, once this field is in the maximum steady state, then only this condition is happening, correct? So this formula we can apply, and this EMF developed is called motional EMF. Even there is a EMF developed in the length of rod during its subsequent motion. तो this EMF is called motional EMF. ये चीज हम conducting rod से पाएंगे. This will not happen in non-conducting like plastic rod or some say dry wood etc. There we cannot get, correct? तो ये चीज हम लोग ध्यान देंगे. Next, once we have this motional EMF arrangement, here this EMF E, it was V BL. This in the terms of magnitude I have written. Otherwise, if I say for any small length of the rod, I have to see this DE will be V cross B dot DL. It is this. And if I integrate both the terms on both the sides, this will give net EMF in the length of rod for any arrangement you can see. This is the proper method for finding the EMF, correct? V cross B dot DL. Final, it is the dot product, so EMF is your scalar quantity. It is a scalar quantity. Also, we should know that if V, B and length L are perpendicular to each other, they are perpendicular to each other, then also the length, this length is actual displacement. It is the displacement vector. It is the displacement between 2 points, between two ends of rod, that will give the EMF. For calculating EMF, you will take the displacement. Meaning that what I am saying, suppose any semicircular figure of the point P and Q is moving towards right. Semicircular figure, it is having the radius R. It is moving in the field with the speed V, and say magnetic field lines, if I assume here they are downward, there are the downward magnetic field lines. Suppose if there are these downward magnetic field lines present, so here EMF across the end PQ, this PQ EMF is not B into V into pi R, but it is B V into 2R. The displacement vector will take across the two ends. This is the displacement vector. The displacement vector we are using for finding the EMF. It is this. ये ध्यान रखिएगा. 2R is displacement. That will take into account. Correct. Suppose it becomes a closed loop. So displacement is 0 and induced EMF will also be 0. That thing also we can prove. So displacement hoga. This thing you have to keep in mind. Like if I am saying any closed loop is moving, say perfect circular loop is moving in a field line like this, what will happen? See, this closed conducting loop is moving in the field line, and say the velocity is V. With the velocity V it is moving. What will happen now? With the velocity V, if I see V cross B, so there will be induced EMF developed. Polarity of the rod, here it will be this. But subsequently you find at the back end, here also one EMF will be developed, and this EMF will be like this. Correct? It is the second EMF, this one EMF. So what you will find, due to two ends, for say it is P and it is Q, two EMF are developed. One is this E, other is this E. If I make a closed loop, ampere circular loop here, so it is plus E minus E, E net. E net in the loop, if I say, this will be what? E minus E, it is 0. E net is 0 in a closed loop. For a closed loop, this EMF, motional EMF will be 0. Hence, we say it is the displacement. With displacement, you can get it correct. Okay. Suppose I say somewhere the arrangement is like this. This type of arrangement is moving. Correct. This is the point P. This is the end Q. And say this length is L. This gap is L by 4. Suppose I say this gap is L by 4. It is present in some external field. If I arrange some external field like this, where it is present, in presence of some external field like this, say B, if it is moving with a speed V, EMF for the end PQ, this is L by 4. So what I will do, only the L by 4 length will take into account, B into V into L by 4. Correct. I am taking the velocity component perpendicular to the length of rod, is also important. Velocity component perpendicular to length of rod is responsible. Length of rod, which causes this EMF to be developed. Velocity has to be perpendicular to the length of rod. Suppose I say this end, say I'd say it is C, it is D. The CD length of the rod is along the velocity. It will not create any EMF. Say this is CD, it is EF. EF length of the rod is also along the length. EF length is also along the velocity. So this also will not create any potential difference. Potential difference will be developed along this. But subsequently for these two, the final displacement which will be remaining is only L by 4. Hence I am taking this as L by 4 length. L by 4 length will create the potential difference generated. So ये concept we can use anywhere and always get the result. Now for the length component, what I was saying, another example I will give. Let us see. Suppose some rod is like this, and this rod is having shape and P, it is Q, say length is L, it is moving with velocity V in some external magnetic field, say it is B. This magnetic field is B at an angle theta. So you see the length of the rod here, the length of the rod PQ, which is having length L, will take some velocity length component perpendicular to the length of rod. So component perpendicular to length of rod is this. This is L perpendicular, and this will be L sin theta. So if I have to see this EMF for the length PQ, I will say it is B into V, and length will be taken as L sin theta. It is L sin theta. This will correspond to the EMF. This thing we have to keep in mind. Suppose I say the same rod, say like this PQ, it is P and Q. It is moved along the velocity and length are in the same direction, and magnetic field is like this. Other case I am taking. Now see the length of the rod, this is in the direction of velocity. So there is nothing like V cross B, there is no space available for the charge move perpendicular to the length. Hence EMF across PQ will be 0. There is no EMF developed across the length PQ. Correct. If it is possible, some charges magnetic force would have happened perpendicular to the length, but there is no space available perpendicular to the length, hence there is no EMF. Correct. Yet even though if I say it was some rectangular rod arrangement like this, and it is moving this way with velocity V, say this length is L and this width is B. say some space existing perpendicular to the velocity. This way I can see the charges, if they are there, so this positive charge will be developed at the top end and negative charge will be at the bottom end. So this way field and force can exist. Na? So this EMF can be generated like this way. I will say here the EMF will be B into V into small b. Suppose it is present in some external field then. Correct. So this thing we have to keep in mind, how to get the EMF developed for any rod and theta angle if it is related. It is this. And this theta is what? Theta is angle between the velocity vector and this length of rod. This thing we can do. So one of the case I mentioned where velocity was constant and theta was also remaining constant, how we get the results. Correct. Next we have a case even when the rod is moving, different portion of the rod are moving with different say velocities like rotation. EMF say across the end PQ when rod is in rotation effect. When the rod is in rotation effect about one end, then what this EMF is. Also that result we can find. Suppose I say this is the rod, just see this point is P, other point is Q, and is present in some external field. This arrangement is present in some external field like this. Correct. If some external field is present, rod is rotated about one end with constant omega. Correct. It's rotating with constant omega. So some length of the rod, how it will create the EMF, we can see. Correct. So some length of the rod, say I am taking this, and the length here from here it is x and small extension is dx. So dx length can develop some EMF. It will have some speed v also. V, every point on the length of the rod will not remain constant. This v at any distance x is omega into x. Omega into x is the velocity in this direction and length dx is in this direction. Both are perpendicular to each other. Hence dE small EMF will be B into V into dx. I will integrate and get the result. If I am integrating, what I will see, EMF E will be B, V is omega x into dx. I will integrate it along the length of rod 0 to L. So I will get the net EMF happening due to this rotation. E PQ length of the rod, if I say it is B omega integration of x dx, and if I say the value, if I am going from 0 to L, it is B omega into x square by 2. Put the values from 0 to L. So net EMF PQ length of the rod, you will get B into omega into L square by 2. So this is the EMF developed. Correct. EMF developed for the length PQ is this. This approach we can make. Correct. So effective length and all EMF will be developed, and also I can see which end will be positive. So V cross B, you see V cross B. So this end of the rod will become positively charged and this end will be negatively charged. So this arrangement we can develop. Okay. EMF will be this. Arrangement को ये approach हम लोग ले सकते हैं, and the rod has to be conducting. Okay. Now what can happen next? Another case I take, suppose I am not rotating about one end, then what? Suppose I say this rod is here and I am making this rotational effect. I am taking another figure. See, this is the rod. Okay. So next, what I am saying, this is the rod, and this rod, if it is made to rotate, if this rod is made to rotate like this about one end, ये ऐसे मैं लेता हूँ, ध्यान देना, इस फिगर को मैं निगलेक्ट करूंगा, तो इस अरेंजमेंट में हम लोग चेक करेंगे, ठीक है। Say this length here from here to here, say it is L by 4. Remaining length is 3L by 4. Rod is rotated about this end. Say this is P, it is Q, and it is O. O is in between. Rod is rotated with omega. This length is L by 4. The remaining here is 3L by 4. Correct. This is 3L by 4. It is present in some external magnetic field. Say like this. Rod is present in some external magnetic field like this. What you will do, the EMF developed. You will see now there are two sections. One is this OP. One arrangement I will see here is OP. E OP I will take one, and other one will be E OQ. So these are the two ends. Accordingly, we will take first segment this one and other one, and accordingly I will put the integration effect and get the result. E for OP if I have to see, it is B omega x dx. I'll integrate it from 0 to L by 4. From 0 to L by 4, this particular length. So this particular length, it can have the speed. See here, the speed V will go like this. Omega will be this way. So velocity will be also in this sense. And V cross B, this end will become positive. Other end will become negative. Correct. Here, what I will say, EMF will be like this. EPQ will be, if I say it is B omega into x square by 2, put the limit 0 to L. Hence, I will say B omega by 2 and L square, it is 0 to L by 4. Here it will be 0 to L by 4. This end is L by 4. So, what I will see? B omega by 2 into square of L by 4. L square by 16. This result we have. Another EMF, this OQ if I say, again will go the same result. What I will have? B omega by 2, 3L by 4 squared. This 0 to, here it is 0 length, and this will go for 3L by 4. Again V cross B, if I see the EMF, it is like this. It is second EMF E2. This EMF was E1. I can see E1 I have got there. E2 if I have to see, the B omega by 2, it is 3L by 4 squared, it is 9 L square by 16, 4 into 4. This result we have. So it is B omega by 2, 9 L square by 16. It is E2. So total EMF, if I have to see, this will dominate. OQ length EMF will dominate over this. So E for the length PQ, if I have to say, what I will say, B omega by 2 times 9 L square by 16 minus L square by 16. Hence it is E for the length PQ, if I say, it is B omega by 2 into, this will be 8 L square by 16. Na? 8 L square by 16 means L square by 2. This further value will be B omega into L square by 4. So this EMF I have got across the length of the rod as per the integration, and also individual EMF values also I have defined. Even when some rod is rotating, we can get the motional EMF, and how we are going, that is also important. Correct. This way we have done. Next case I will take some other elements also. Next thing I can do is, say one rod is in the shape of L. L shape rod is rotating about end O. Say this point is O, it is P and it is Q. Now what I have, this OP length, this OP length is non-conducting. OP length, but this length is conducting. So, what can be the EMF developed for the EPQ? EMF in PQ length, how it will be obtained? So, this rod arrangement, if I say is rotating at 90 degree here, these two conducting and non-conducting are 90 degree, and there is some field present in this direction. Some field is present in this direction, correct? Now, if I have to see only the EMF in the portion PQ, what it will be for the PQ. Now, first of all, we see the length OP. OP length is non-conducting. This length is conducting. What can I do? I can take the EMF for the whole length EOP. Initially, I can take EOP if the whole part was conducting, and in that I can subtract EOQ part. This I can subtract. So, first of all, if it is conducting, I will say EOP length EMF for this length L. Say this length was L, another length is also L, both lengths are L each. EOP length EMF will be B omega L square by 2. EOP length EMF will be B omega L square by 2 had it been conducting. Now, for EOQ, if I see the EMF for EOQ, I am taking the whole portion as conducting, and then I will subtract this portion, I will get the remaining EMF. So, that way I am making the approach. EOQ, the displacement between these 2 points, that will be L root 2. So, it is B omega L root 2 ka squared by 2. L square by 2. This is the final result we are getting with the help of integration. If I go like that, so EOQ, if you see what it will be, B omega L square, and EPQ, if I integrate EOP was this, hence EPQ will be EOQ minus EOP. EOQ, if you see, it is B omega L square minus EOP is B omega L square by 2. It is E for the length PQ. Hence, this value is B omega into L square by 2. This is the EMF developed in the length PQ. For the length PQ, I am getting the EMF. So, for the part of the rod, if I had to see, so this arrangement could have been, and even here I am saying, if the full length of the rod was rotating, EOQ, this is also the EMF for L-shaped rod. I can say for L-shaped rod, if whole part was conducting, if both the parts were conducting, non-conducting and conducting, both were conducting, then the EMF would have been this. EOQ EMF would have been this, and one part also we have seen, na? So, that pure conducting part PQ also I got the result. So, this way also method is there for rotating rods and arrangements. How do we get the EMF? All this was for motional EMF developed in the length of the rod. Different sections, integration, all the part I have discussed. Okay. Next we have one more case, that is EMF due to time varying magnetic field. So, there is always induced EMF E dash due to time varying magnetic field. Time varying magnetic field. So, time varying magnetic field can always induce the electric field. This result also we can make, time varying magnetic field. What does it say? Suppose there is some region of space, say this region of space I am making, and there are some field lines existing with time. These field lines are existing with time, but they are varying. Field line in this space, say it is varying as B naught times 1 plus alpha into T. This way field is varying with time in this space, not remaining constant. alpha is some constant, t is the time, B naught is also constant. If some field is varying like this, and always we can find there will be some hypothetical field, induced field lines developed, meaning that if I put a conducting ring in this space, there is no motion as such, only field lines are varying. I can say that with the time increase, magnetic field is increasing here in this space. So if I take any x length here, for this x length less than the radius, suppose the radius was r and this x length is like this, x is less than r. In this particular wire, say it is a conducting wire, placed or not placed, there always be tendency of induced field lines. Induced field lines will create E dash will correspond I dash, because field is increasing, flux is increasing. This will correspond B dash opposite to this one. So B dash shall be opposite to this one, means outward. B dash outward means your I dash shall be anti-clockwise. So this way the sense of current will be flowing. If the sense of current I dash is like this, so induced field lines in this length, that will also be going this way. E dash also will be going this way. And this induced field lines along this induced field lines E dash, if I say line integral E dot dl in the closed loop is not 0. These field lines E dash, they are not conservative in nature. Earlier we have seen in the first chapter electrostatics, field lines were conservative. These field lines are not developed due to presence of charge. They are being created in these field lines due to flux increase or decrease, flux change. So these field lines are E dash. It is what I say, it is non-conservative. They are non-conservative. So work done by these field lines in a closed loop will not be 0. Hence EMF developed will also not be 0. I can say the basic relation will be that experimentally has been found. E dash is not 0. So what it will be? It will be the EMF integration of E dash into dl, that will give EMF if circumference field magnitude everywhere at these points they are remaining constant E dash. Hence I will say it is E dash into circumference length is 2 pi x. E dash into 2 pi x will be the EMF is equal to EMF. EMF will be dB by dt, flux change. If I go for this, so dB by dt, just you see, for the flux change I can say dB by dt, if you see here, the B naught into alpha, one differential is 0. Alpha into t, the result will be B naught into alpha. So dB by dt is B naught into alpha, this you can do. Result is B naught into alpha. So here result I will put here, d by dt is B naught into alpha, this is the flux change, into area. Area is what? Pi x square, pi into x square. So dV by dt into area of the loop is the rate of change of flux is equal to EMF developed. So this result I can make. Induced field lines, they will create a field here. Again I write at the top, it is E dash into 2 pi x. This you write here B naught alpha into pi x square, Further if we summarize, E dash value will be what? E dash value will be B naught alpha by 2, correct? B naught alpha by 2 into x. So this is the expression of field, induced field lines E dash. E dash field lines are like this. For any x less than radius, E dash field lines will be going this way. So this result I can make. Induced field lines for any region between 0 to radius of the loop. E arrangement it will be count, correct? E dash is varying linearly with x, rest of the terms are remaining constant. Now I come to the next piece and see the result. So I am saying that E dash is equal to B naught alpha by 2 into x. This result we had. One step moving forward, what we'll see it was the region of field where it was varying, radius was r, I am making a shorter figure, and field lines they are like this. Suppose I take the field lines, they are existing here in this space Okay, this way they are present. This B lines value are B is equal to B naught times 1 plus alpha into T. Now, this thing we have. For this part X less than R, that I have done. This part I have defined E dash. So this E dash here I have defined function of X. Now we'll take another position for X more than R. This X is more than R. Then what will be the expression of field lines here for X more than R if I am taking like this. Again I will take the loop, closed loop like this. For this region, for X more than R, second case I am taking, again the field lines will be created because flux is increasing. So induced field lines and current will go like this. I dash or E dash sense will be such that your B dash induced is again opposite to the present field. So I'll say E dash into circumference length is 2 pi x induced EMF developed. That will be equal to dV by dt flux change into area. Correct? This thing I do. The dV by dt field is changing only in this area. No field is existing between capital R to X here. No field. Here B is 0. So I will see the flux change only in the region 0 to R. So dV by dt into area will be pi R square not X square. And here this X, I say this X is more than radius. Also we have to keep in mind. So what result I will have, just see E dash into 2 pi x dV by dt. If you see, that was what? B naught into alpha into pi R square. So E dash, if you see here, it is B naught into alpha, pi got cancelled. This R square by 2 times 1 by x. E dash is inversely proportional to x. What I got? This E dash value, I can say it is varying 1 by x. Earlier E dash was varying linearly to the x. These are the two factors, 1 by x and that is proportional to x. If I have to draw the graph also correspondingly I can draw for the field lines here. You can see this is the E versus x. Induced field lines versus x. If I have to draw the graph, initially it was varying this, then again it will go inversely. So this is for x less than R and this is for x more than R, inversely proportional. Here is varying inversely to the x. For time varying field, this expression is important, and also we have seen dB by dt. dB by dt was remaining constant. Here if I say this dB by dt was remaining constant, this is B naught into alpha, this value was constant, correct? This thing can be applied and we can get the result. For any EMF, and also I can say for x equal to R, this field induced is maximum. The maximum field induced will be here. And the field is increasing radially outward till the boundary where the field is existing, maximum position of x. So this graph and result will tell you the induced field lines, correct? One more case related to this time varying electric field and magnetic field, I can say it. Means here the cause is that this E dash is non-conservative and is produced by time varying magnetic field. Now one more case I gave you, very interesting, this thing happens. Suppose the same region of space of the radius R, field lines are present in the space like this. These are the field lines, okay. These field lines have the value expression B is equal to B naught times 1 plus alpha into T. This we have, correct. Now I create some values. I have drawn the graph also. Suppose there are some circular loops, independent loops like this. This one at the position distance say x1. Second one some symmetrical here. Same figure if you see it is x2. And third one if I say here it is present and say it is the distance is x3 and x3 I say is more than radius, correct? Suppose this is the R. So there are three loops, first loop, second loop and third loop. These are the three loops. I have drawn the graph of E dash versus X, just you see E dash versus X. Graph was like this and there it was going like this way. This was the graph we have seen. But if I say all the three loops are identical, I will say the field strength E1 dash will be less than E2 dash. Means E2 dash will be more, for it is readily more distant than X1 because it is at the position X1 and it is at the position X2. And X2 is more than X1, E2 dash will be more than E1 dash. This result we have, correct? Meaning that if I say here the field line is weaker compared to this, but if all the three figures are same, what I will say, EMF developed E1 and E2, E1 and E2 for the EMF at these two places. E1 and E2 EMF, are they same or not? From the field lines I can say if the figure is symmetrical they should be same. But this EMF from the field lines I say that the EMF will not be same because this is closer, E1 is less than this. But what we find, the flux change in these independent loops, that will be countable, hence E1 will be equal to E2 because what I say, dB by dt, the rate of change of flux, it was remaining constant into area is remaining same. So any place dB by dt at both the places is same and area is same. So induced EMF will be equal. So it is not following the field lines because these are the independent loops. Even for the third place, if I say here, even though there was field existing, here E3 EMF will be 0. Despite that E dash is not 0 in third place, E dash 3 is not 0. Meaning that governing factor for induced EMF is flux change and not the induced electric field lines, because all the three loops they were independent. Always we should keep in mind that EMF is induced primarily due to rate of change of flux, correct? So this approach, this idea we can make, and from there we can get this question done. I think it is clear, this approach for induced field lines, how we are getting. One more case I will discuss, quite interesting. Let us see what is that. The time varying electric field lines. Suppose EMF in the length of rod I will take. This is the case. Arrangement is like this. Once again I will make this figure. Suppose I say this is the loop, correct? And in this loop I am putting a rod like this, and this is the center O. This is the rod, conducting rod P, and this length is Q. So PQ is the conducting rod, O is the center, and there are some field lines present. Field lines are present here, correct? And radius of this arrangement is R. Field lines are present with the same factor, B is equal to B naught times 1 plus alpha into T. This arrangement is happening. Field lines are this. There is a conducting rod of length L present and is forming angle theta. We have to find the induced EMF in the length PQ of the rod, what it will be, and field lines are present here. The induced EMF, if I have to see in the length of rod, what can I say? For any arrangement, if I go like that, what I will form, what can I say? How this time varying field can create a EMF. So just see this value. If I take some arrangement like this way, just see any length on the rod. If I take any length on the rod, what I have, say it is this, say radius is x. For a radius x, which one end here it is falling, and I take small length of the rod dl. here like this. DL is this way, X is this one, correct, E, and field lines I say here, the field lines they will be going like this. So these are the field lines are going like this way, induced field lines will happen this, and these field lines, magnetic field lines are this, but this is the direction of induced field lines here. If it is changing with time, you see induced field lines, because magnetic field is increasing with X in the forward direction. So induced field line will oppose and that will go outward. For that magnetic field lines E dash will be this. If E dash is happening this way, so DL length of the rod, if I have to see, just see, if the DL is this, I will take some small part here. Suppose I say this angle is theta, suppose this angle is theta, some small part here, it will form an angle d theta. This is the angle d theta. Just see, this is theta, but this is d theta. Now what can I take this arrangement? If I take, just see, there will be some element here. So if I have to see the EMF developed here, DE, for the DE EMF developed, what can I say? The value will be dB by dt, rate of change of the field, into area. For this element, what is the area bound? If I see the area, what can you see? This is the length L, X, this is the length X, and here you see it is the DL, but this is a small triangle, this is the triangle. So this triangle, what can I say, the area, d by dt into small area dA. What you will write for dA? dA is a small triangle, half of base into height, half of base factor is what? It is X. It is this X, base is this X, into height. For this, if I take the height will be this length, curve length of E lines. It will not be DL, it will be the curve length, but area bound will be for the triangle. So I can say here the length taken will be half of X into what I will have, this X into d theta, because this is theta, this small angle is d theta. This area I have to take for the triangle. Area bound will be half of X into X d theta, correct. Half X into d theta, this result will give you the area bound. If I integrate this term, what I find here, from here, dB by dt, it is remaining constant, it is B naught into alpha, and this value is constant. So from here I can see the total EMF E will be equal to d by dt is B naught alpha, and integration of dA area bound by the length of the rod with point P, area of the triangle. So if I take the total area EMF, if I integrate, the total area will be total length. Here I can take the total area will be this dA area. If I integrate, integration of area dA, and that will be area of triangle, just see, O, this point is O, this is PQ, area of triangle OPQ. This thing I can do. What will take? Area of triangle OPQ. Hence I will say this EMF is B naught alpha, and this area is area of peak OPQ, area of triangle OPQ. This result I can see. For area of triangle, you can easily see what we have. All the side and length they are mentioned. Say this is R, and this length, if I take this length is L by 2, because total length of the rod was L. So this is L by 2. So what I have, this length is R, this length is L by 2. So this will be other length, this will be under root of R square minus L square by 4. Correct. So total EMF, if I have to see, also I can write. So total EMF, that will be what? EMF E for the length PQ. What I will write? It is B naught into alpha into multiplied with the area. Area will be half of base into height. It is L by 4. Half of base into height is under root of, just see, r square minus L square by 4 into 2, because they are two types, this and this, both the side, into 2 if I am doing. So this further value will be what? B naught alpha into L by 2, the into L by 2 under root of r square minus L square by 4, r square minus L square by 4. This result we have. Further if I write, it is B naught into alpha into L by 2. If I see, it is what? In under root it is r square minus L square by 4. So this is the result of EMF developed. It is the EMF developed in the rod PQ. The PQ rod EMF developed, final result I am writing, it is this, just see. ये result आपका आएगा. For the PQ rod EMF developed, again I will write here, EPQ will be what? Just see, B naught alpha by 2 times under root of r square minus L square by 4. So this was the case. Just with the help of integration and some element done, I have taken the area bound this triangle. This triangle is enclosing containing the point O vertex of the circle, and this triangle formed with the base length of the rod. Always this you can apply for any of the cases for area bound on the conducting rod PQ. Correct. All this was for EMF, motional EMF developed due to time varying magnetic field. So these cases are there for the flux change. So motional EMF I have done, and this thing. Further, there is another property of inductance. Inductance and other things that I will do in the next class. तो इसमें हम लोग motional EMF all that I have discussed. Thank you.